For 50 years, astronomers searched for something that had to be there. Every supermassive black hole that actively feeds on its surroundings does the same thing. It pushes material outward even as it pulls material in. A wind. A signature of activity, visible from any large telescope pointed in the right direction. Every supermassive black hole studied so far, except, it seemed, our own. At the center of the Milky Way sits an object roughly 4 million times heavier than our Sun, compressed into a region smaller than the orbit of Mercury. For half a century, every search for its wind came back empty. Weeks ago, that finally changed. By the end of this video, you will understand exactly how astronomers found that wind after 50 years of searching. You will understand what a separate team discovered about a catastrophic event in Sagittarius A's recent past, one that contradicts everything we thought we knew about how quiet it has always been. And you will understand why a small but serious group of scientists now argues we may have misidentified what's actually sitting at the center of our galaxy. None of this is speculation dressed up as fact. Every claim in this video traces back to a published study, a named telescope, or a peer-reviewed measurement. Where the science is still genuinely unsettled, we'll tell you so directly. If this kind of deep, fact-checked exploration of space is something you enjoy, take 2 seconds to like or subscribe. It genuinely helps a channel like this grow. Let's start at the beginning. 26,000 light-years separate us from the center of our galaxy. Light, the fastest thing in existence, takes 26,000 years to cross that distance. The most precise measurements, using a technique that tracks individual stars in tight orbits around the galactic center, place the figure closer to 27,000 light-years. Either way, the object we're about to study is so far away that the light reaching our telescopes tonight left its source before the construction of the first cities on Earth, and yet we can study it in extraordinary detail. That tells you something about its mass. Sagittarius A, the name comes from its position in the constellation Sagittarius, and the asterisk marks it as an astronomical radio source, contains the mass of roughly 4 million suns, not spread across a region the size of a solar system. Compressed into a space with a diameter of about 52 million kilometers. For comparison, Mercury's closest approach to our Sun is about 46 million kilometers. The entire mass of 4 million stars like ours fits inside a sphere smaller than Mercury's orbit. Here's a way to feel that number. If you shrank the Sun down to the size of a marble, Sagittarius A, at the same shrunken scale, would still need to contain the mass of 4 million marbles packed into a ball you could hold in 2 hands. That's not a star. That's not a dense star cluster. Calculations using Einstein's general relativity, combined with decades of orbital data, leave essentially one explanation standing: a black hole. Put another way, our galaxy contains somewhere on the order of 100 to 400 billion stars, spread across a disk roughly 100,000 light-years wide. Every one of those stars, including our Sun, is slowly orbiting the galactic center, held in its path by the combined gravity of the entire galaxy, but with Sagittarius A sitting as the single most concentrated source of mass anywhere near that center. We are, in a very literal sense, circling it right now, just as we always have, at a perfectly safe distance of roughly 26,000 light-years. But here is the part that doesn't fit the pattern. Every other supermassive black hole astronomers have studied in detail, at the centers of other galaxies, behaves like a furnace. Material spirals in, heats to extreme temperatures, and radiates enormous amounts of energy outward, in some cases outshining every star in its host galaxy combined. Some of that infalling material gets redirected into powerful jets and winds, blasting outward at near light speed. Sagittarius A does almost none of that. It is, by a wide margin, one of the dimmest supermassive black holes ever measured. For an object with its mass sitting so close to us, astronomically speaking, practically in our backyard, it should be one of the easiest, brightest black holes in the sky to study. Instead, it has spent decades behaving like it's barely awake. That contradiction is the question this video is built around. Is Sagittarius A simply a quiet black hole, fundamentally calmer than its cousins elsewhere in the universe? Or is quiet the wrong word, a misleading first impression created by the limits of our instruments, hiding a much more violent and complicated object underneath? Recent discoveries suggest it's the second one. But before we get to those discoveries, it helps to be precise about what we're actually describing when we say black hole, because the term gets thrown around loosely. A black hole isn't a hole in any literal sense. It's a region of space where so much mass has been compressed into so small a volume that the resulting gravity prevents anything, including light, from escaping past a certain boundary, called the event horizon. Cross that boundary, and there is, as far as our current physics can describe, no path back outward. Outside it, however, gravity behaves exactly the way Newton and Einstein both described it. A black hole doesn't reach out and suck in everything nearby, the way it's sometimes shown in movies. An object orbiting at a safe distance from Sagittarius A is no more in danger of falling in than the Earth is in danger of falling into the Sun. The danger only begins if you cross that one-way boundary. Black holes come in different size categories. Stellar mass black holes, formed when massive stars collapse at the end of their lives, typically weigh somewhere between a few and a few dozen times the mass of our Sun. Supermassive black holes are a different category altogether, millions to billions of solar masses, and they appear to sit at the center of nearly every large galaxy astronomers have studied in enough detail to check, including our own. Nobody has fully solved how supermassive black holes grew so large, so early in the universe's history. That question sits outside the scope of this video, but it's worth knowing it's still an open one across the field. The idea itself is older than you might expect. Black holes fell directly out of the mathematics of general relativity almost as soon as Einstein published the theory in 1915. The physicist Karl Schwarzschild found a solution to Einstein's equations, describing exactly this kind of object within months. While serving on the German front during the First World War, for decades, most physicists treated the result as a mathematical curiosity rather than something that could exist in nature. The term black hole itself didn't enter common use until the 1960s, popularized by the physicist John Wheeler. It took until the final years of the 20th century for observational evidence, not equations, but actual telescope data, to drag the concept out of theory and into confirmed reality. Sagittarius A became the single best piece of that evidence. With that groundwork laid, here's the central tension this video is built around. Is Sagittarius A simply a quiet black hole, fundamentally calmer than its cousins elsewhere in the universe? Or is quiet the wrong word, a misleading first impression created by the limits of our instruments, hiding a much more violent and complicated object underneath? Let's see how astronomers figured that out, starting with how we found Sagittarius A in the first place. You cannot photograph a black hole directly. By definition, no light escapes it. So for most of the 20th century, the idea that something monstrous sat at the heart of our galaxy remained exactly that, an idea, inferred indirectly, but never confirmed. The trail actually starts decades earlier than you might expect, with a discovery nobody was looking for. In the early 1930s, a young engineer named Karl Jansky was working for Bell Telephone Laboratories, trying to track down the source of static interference plaguing transatlantic radio communications. In the process, he picked up a faint, steady hiss of radio noise coming from a fixed direction in the sky, toward the constellation Sagittarius, toward the center of our galaxy. Jansky had accidentally founded the field of radio astronomy. It would be another 4 decades before anyone understood exactly what was generating that signal. The first real clue came in February 1974. Astronomers Bruce Ballack and Robert Brown, using a radio interferometer at the National Radio Astronomy Observatory in Green Bank, West Virginia, detected an unusually bright, unusually compact source of radio emission sitting almost exactly at the dynamical center of the Milky Way. It wasn't obvious at first what they'd found. Ballack later described the result simply as exciting, a strong, sharply defined signal where theory predicted something massive ought to be, but with no way yet to confirm what that something actually was. The object didn't even have its now familiar name at first. It took another 8 years, until 1982, for Robert Brown to coin the designation Sagittarius A, borrowing the asterisk notation from atomic physics, where it's used to mark an atom in an excited, energetic state. Brown thought the analogy fit, a compact source embedded inside a larger structure, Sagittarius A, and seemingly feeding energy into its surroundings. The name stuck and has been used ever since. Knowing a bright radio source sat at the galactic center wasn't the same as knowing what it was, though. That answer required a completely different kind of evidence, not radio waves, but the movement of stars. Beginning in the early 1990s, 2 independent research teams, one led by Reinhard Genzel in Germany, the other by Andrea Ghez in the United States, pointed some of the world's most powerful telescopes at the crowded, dusty region at the center of the Milky Way, and started tracking individual stars year after year as they moved. Genzel's team worked primarily with the Very Large Telescope in Chile. Gez's team relied on the Twin Keck telescopes in Hawaii. Both groups faced the same fundamental obstacle. The galactic center is obscured by thick clouds of interstellar dust, invisible in ordinary light. The breakthrough came from adaptive optics, technology that uses deformable mirrors, adjusted many times per second, to cancel out the blurring caused by Earth's atmosphere, combined with infrared observation that can punch through dust that blocks visible light entirely. For the first time, individual stars deep in the galactic center came into sharp enough focus to track precisely, year after year. This wasn't a quick project. Stars near the galactic center move fast, but fast on a galactic timescale still means decades of patient observation. The 2 teams worked independently, using different telescopes, different instruments, and at times a genuine sense of competition, each pushing to publish first, each occasionally skeptical of the other's results. That rivalry, as it turned out, became one of the discovery's greatest strengths. When 2 competing groups, using different equipment on different continents, kept arriving at the same answer, it gave the result a kind of credibility that a single team working alone could never have produced on its own. One star in particular, designated S2, sometimes called S02, became the key to the entire investigation. S2 orbits something invisible roughly every 16 years, a blink of an eye by stellar standards, and proof by itself that whatever it orbits is both massive and unimaginably compact. Here's why that orbit mattered so much. Using nothing more exotic than Kepler's laws, the same equations that describe how planets orbit the sun, both teams calculated the mass needed to whip a star around that fast, in that small a space. The answer, refined over decades of additional observation, converged on roughly 4 million solar masses, confined to a region not much larger than our own solar system. That alone was extraordinary. But the orbit of S2 gave astronomers something even more powerful, a natural laboratory for testing Einstein's general relativity in conditions Einstein himself never could have imagined. In 2018, as S2 made its closest approach to Sagittarius A, a point in its orbit where it's moving at nearly 3% of the speed of light, astronomers detected something general relativity predicts, but that simpler Newtonian physics does not: a gravitational redshift. Think of it this way: light is a wave, and gravity can stretch that wave out as it climbs away from a massive object, shifting its color slightly toward the red end of the spectrum. The same basic idea behind the more familiar Doppler shift you hear in a passing ambulance siren, but caused by gravity instead of motion. Newtonian physics doesn't predict this effect at all in the way general relativity does. The measurement, when it came in, matched Einstein's prediction. This wasn't a small finding tucked into an obscure journal. In 2020, the Nobel Prize in Physics was split between 3 people for this exact line of work. Reinhard Genzel and Andrea Ghez each received a quarter of the prize for the discovery of a supermassive compact object at the center of our galaxy, meaning Sagittarius A itself, confirmed at last as something other than just a bright radio source. The other half of the prize went to Roger Penrose for proving decades earlier, through pure mathematics, that black holes are not just a theoretical curiosity, but a robust, near-unavoidable prediction of general relativity whenever enough mass collapses into a small enough space. By the end of the 2010s, the case was about as strong as indirect evidence could make it. Something with the mass of millions of stars sat at the center of our galaxy, packed into a space too small for almost anything else to explain. Stars orbited it at extreme speeds. Light bent and stretched around it in exactly the way Einstein's century-old equations predicted. There was just one thing missing. Nobody had actually seen it, not even in shadow. That changed in 2022. But getting that image took a different kind of effort entirely, and it nearly didn't work. In April 2019, the Event Horizon Telescope collaboration released the first image ever taken of a black hole. It wasn't Sagittarius A. It was the supermassive black hole at the center of a galaxy called M87, roughly 55 million light-years away, over 2,000 times farther from us than our own galactic center. That might seem backward. Shouldn't the nearer black hole have been easier to photograph first? It's a fair question, and the answer says something important about why imaging Sagittarius A turned into one of the hardest problems in observational astronomy. The Event Horizon Telescope isn't a single instrument. It's a network of radio observatories spread across the planet, from Antarctica to Hawaii to Spain, 8 stations in total at the time of the first observations, linked together using a technique called very long baseline interferometry. Each site records incoming radio waves with extreme precision timing, governed by atomic clocks accurate enough to stay synchronized to within a fraction of a billionth of a second. By later combining the recordings from every site, the network effectively becomes a single virtual telescope, roughly the size of Earth itself. That's the only way to achieve the angular resolution needed to see something as small, in the sky, as a black hole's shadow. A resolution the collaboration has compared to being able to read a newspaper in New York while sitting at a cafe in Paris. M87's black hole is roughly 1,500 times more massive than Sagittarius A, which makes it enormous. But it's also far enough away that, from Earth's perspective, it appears at a similar apparent size in the sky to our own galactic center's black hole. In theory, that should have made them comparably difficult to image. In practice, M87's black hole had one major advantage. It barely changes while you're looking at it. Because of its enormous size, gas orbiting M87's black hole takes days to weeks to complete a single loop. Sagittarius A is a different story. It's so much smaller that gas in its immediate vicinity completes an entire orbit in roughly half an hour. Imagine trying to take a long-exposure photograph of someone running sprints versus someone going for a slow walk. The data collection for Sagittarius A took place over multiple nights, but the source itself was shifting and flickering even as the telescopes watched, breaking the normal assumption that the thing being imaged holds still during the exposure. Astronomers had to develop entirely new computational techniques and test thousands of simulated black hole models against the data, just to reconstruct a stable, trustworthy image out of a target that wouldn't stop moving. It took 3 additional years of analysis after the M87 image before the team felt confident enough to release a result for our own galaxy's black hole. On May 12, 2022, they did. Before that release, the collaboration put the data through a deliberately paranoid verification process. Multiple independent teams reconstructed images from the same raw data without comparing notes with one another, specifically to make sure no single group's assumptions were quietly shaping the result. Only after those independently produced images converged on the same basic structure, a bright ring around a dark shadow, did the collaboration treat the result as solid enough to publish. It's a useful reminder of how this kind of science actually works. Not a single dramatic snapshot, but years of cross-checked, independently reproduced analysis before anyone is willing to call something confirmed. The image showed what astronomers had expected in principle, but had never actually seen: a bright, asymmetric ring of glowing gas measuring about 51 micro-arcseconds across, encircling a dark central region, the shadow cast by the black hole's gravity bending and trapping light around it. You're not looking at the black hole itself, you're looking at the silhouette it leaves in the glowing material around it, a picture, essentially, of an absence. What made the image scientifically powerful wasn't just that it existed. It was that the size of the ring matched, almost exactly, what general relativity predicted it should be, based on the mass and distance already established through decades of stellar orbit tracking. 2 black holes of wildly different size, one over 1,000 times more massive than the other, both produced shadows consistent with the same 100-year-old equations. As one of the project's scientists put it at the time, the agreement told them that general relativity governs these objects up close, even though plenty remains unexplained about the environment surrounding them. 2 years later, in 2024, the same collaboration returned with a follow-up, a polarized image of Sagittarius A, revealing strong, organized magnetic field lines spiraling at the very edge of the black hole, twisting outward from the dark central shadow in a pattern resembling a pinwheel. The structure looked remarkably similar to the magnetic fields seen years earlier around M87's much larger black hole, another point of similarity between 2 objects that on paper shouldn't behave alike at all. Organized magnetic fields like these matter because they're thought to play a role in launching the jets and winds seen around other active black holes. Which made it stranger still that, despite having a magnetic structure that looked primed for exactly that kind of activity, Sagittarius A still showed no confirmed outflow of its own. So by the mid-2020s, Sagittarius A had gone from an inferred mass to a confirmed object via stellar orbits, to an actual photographed shadow with measurable magnetic structure. The case for supermassive black hole looked airtight, and yet, even with all of that confirmed, one stubborn problem remained completely unresolved. The object photographed in that 2022 image was almost insultingly dim compared to what theory said it should be. Here's the puzzle that frustrated astronomers for decades, even after Sagittarius A's existence stopped being in doubt. It doesn't behave like a black hole its size should. Supermassive black holes at the centers of other galaxies are often the brightest single objects in their entire galaxy, sometimes brighter than every star in that galaxy combined. The mechanism is straightforward in principle. As gas and dust spiral toward a black hole, friction and compression heat that material to extreme temperatures before it crosses the event horizon. The result is enormous amounts of radiation blasted out across the electromagnetic spectrum, sometimes accompanied by jets of particles moving at a meaningful fraction of the speed of light. Sagittarius A does almost none of this, despite containing 4 million solar masses. It ranks among the dimmest supermassive black holes that astronomers have ever measured, visible to us mainly because it happens to be so close, not because it's putting out anywhere near the energy theory says an object of its mass could produce. Physicists have a benchmark for this, the Eddington luminosity, a theoretical ceiling on how bright an object can shine while still being held together by gravity rather than blown apart by its own radiation pressure. Many actively feeding supermassive black holes shine at a meaningful fraction of that ceiling. Sagittarius A operates at a tiny fraction of a percent of it, closer, proportionally, to a nightlight than to the furnace its mass should theoretically allow. For years, the leading explanation was simply starvation. Sagittarius A isn't actively feasting on large quantities of infalling gas the way some of its more dramatic cousins are. Less fuel in, less radiation out. That explanation works as far as it goes, but it left a second, more specific puzzle unanswered. If material is occasionally falling in, where does it go? Active black holes elsewhere don't just absorb everything that approaches. They redirect a portion of it outward, as outflowing winds and jets, even during relatively quiet feeding episodes. For 50 years, despite searching, nobody could find any equivalent outflow coming from Sagittarius A. It looked less like a sleeping giant and more like an object that had simply never been particularly active in the first place, a strange exception to how every other supermassive black hole seemed to work. That 50-year absence is, in fact, the very mystery this video opened with. And as you'll see later, the explanation that finally emerged this year wasn't simply the wind was too faint to detect. It pointed toward something stranger, evidence that Sagittarius A may not always have been this calm at all. But before we get there, it's worth pausing on one more layer of this puzzle, one that goes deeper than just why is it so quiet? Before the stellar orbit evidence became overwhelming, scientists seriously considered whether the object at our galactic center might not be a conventional black hole at all. A cluster of extremely dense, dead stars, neutron stars, white dwarfs, the collapsed remnants of stars that ran out of fuel long ago, packed tightly together into the same small volume, was one early candidate. It's not an unreasonable idea on its face. The galactic center genuinely is crowded with old, dense stellar remnants. The problem is stability. Calculations showed that a cluster dense enough to explain the observed mass and orbits would be gravitationally unstable, with its members colliding and merging on a timescale far shorter than the age of the galaxy. Run the clock forward, and a cluster like that collapses into a black hole anyway, so even if one existed in the distant past, we wouldn't expect to find one still intact today. Other, more exotic ideas were proposed too. One was a hypothetical, extremely dense ball of sterile neutrinos, a theorized type of particle that, unlike the neutrinos we've actually detected, would barely interact with anything else at all, making it a candidate for invisible, gravity-only mass. Another was a so-called boson star, a theoretical, smooth ball of bosonic particles, held together by gravity and quantum effects rather than by the kind of nuclear physics that powers ordinary stars, dense enough to mimic a black hole's gravitational pull without an event horizon at all. Each of these alternatives ran into the same wall. The precise orbital data from stars like S2 showed no sign of the kind of internal structure, drag, or instability you'd expect from a spread-out cluster or an extended ball of exotic matter, rather than a single, compact, point-like mass. By the early 2020s, the scientific consensus had settled firmly on supermassive black hole, confirmed by stellar orbits, by gravitational redshift matching Einstein's predictions, and finally by direct imaging, which is exactly why a study published in 2026 proposing yet another alternative explanation caught so much attention. We'll get to that along with the explosive discovery about Sagittarius A's hidden past and the long-awaited detection of its missing wind later in this video. For now, hold on to the contradiction we've built so far. Every confirmed piece of evidence, the orbits, the redshift, the photographed shadow, the magnetic fields, points to a textbook supermassive black hole. And yet, for 50 years, this particular black hole has refused to act like one. What changes that picture isn't a single new discovery, but three separate ones, arriving in rapid succession in 2026, each from a different team, using different instruments, looking at completely different kinds of data. One found a pulsar and a binary star system tucked closer to Sagittarius A than anyone expected to survive. Another, using a brand new X-ray observatory, found evidence the black hole was once blazing thousands of times brighter than it is now. And a third, after 50 years of searching, finally caught the missing wind itself. Let's go deeper into what astronomers found when they finally figured out why Sagittarius A has been hiding its past. We left off with a promise, 3 separate 2026 discoveries that would force a complete reconsideration of what's actually happening at the center of our galaxy. Before we get to them, there's one more piece of the immediate environment around Sagittarius A you need to understand, because every discovery that follows depends on it. It's called the S cluster, and it's one of the strangest neighborhoods in the galaxy. Picture the region within a few light days of Sagittarius A, astronomically tiny, a volume of space you could fit comfortably inside our own solar system. Packed into that space are well over 100 fast-moving stars, all locked into tight, looping orbits around the black hole. Astronomers have been cataloging and tracking members of this cluster for more than 2 decades now, refining their orbits year after year, using the same adaptive optics techniques that first revealed S2's path back in the 1990s. Each new generation of instruments has pushed that catalog further, turning up fainter, closer, and stranger objects the deeper astronomers look. We've already met one resident of this cluster, S2, the star whose 16-year orbit first allowed astronomers to weigh Sagittarius A and confirm Einstein's predictions about gravitational redshift. But S2, it turns out, isn't even the most extreme member of this neighborhood, not by a wide margin. In 2022, a research team from the University of Cologne and Masaryk University, led by astronomer Florian Paesker, announced the discovery of a star called S4716, and it broke every record the S cluster had previously set. S4716 completes a full orbit around Sagittarius A in just 4 years. At its closest approach, it comes within about 100 astronomical units of the black hole, roughly 15 billion kilometers, which sounds enormous until you remember that our own sun orbits the galactic center from a distance of 26,000 light-years. On a cosmic scale, S4716 isn't just close. It's practically grazing the black hole's doorstep. To pull off an orbit that tight in that little time, S4716 has to move fast, and it does. At its closest pass, the star reaches a velocity of roughly 8,000 kilometers per second. That's about 2% of the speed of light. For comparison, the fastest spacecraft humanity has ever built top out at a small fraction of that speed. S4716 hits it as a matter of routine, once every 4 years, like clockwork, simply by being caught in the gravitational grip of Sagittarius A. It isn't even alone in pushing the limits of that cluster. The same research group also tracks a star called S4714, which swings even closer to Sagittarius A at its nearest approach, but on a longer, more elongated 12-year orbit, rather than S4716's tight 4-year loop between them. These two stars define the current edges of what astronomers have confirmed survives in the immediate vicinity of the black hole, objects skimming past at a meaningful fraction of light speed. On orbits so compact they'd fit within the orbit of Mars if you transplanted them into our own solar system. Here's where the story gets genuinely puzzling, though. Stars aren't supposed to form anywhere near this close to a supermassive black hole. The tidal forces in that environment, the difference in gravitational pull between the near side and far side of any object, are intense enough to tear apart the slow, diffuse clouds of gas that normally collapse to form new stars. By the standard model of star formation, the region S4716 currently occupies should be far too violent a neighborhood for a star to have been born in. So how did it get there? The leading explanation, proposed by the Discovery team, is migration rather than local formation. S4716 likely didn't form in its current tight orbit at all. Instead, the working hypothesis is that it formed farther out, in a somewhat calmer region of the S cluster, and was gradually dragged inward over time, nudged closer and closer to the black hole through repeated gravitational interactions with other stars and objects in the crowded cluster around it. It's a process similar in spirit to how some planets in young solar systems migrate inward toward their host star through interactions with surrounding debris, just on a far more extreme scale and over a much shorter span of cosmic time. This single discovery reframed how astronomers think about the entire S cluster. It isn't simply a fixed collection of stars sitting in stable, unchanging orbits. It's a dynamic, evolving system, where gravitational interactions are actively reshuffling which stars sit closest to Sagittarius A at any given moment, and where the black hole's influence extends far enough to drag a star into an orbit that takes it sweeping past at a meaningful fraction of light speed once every 4 years. Indefinitely, keep that picture in mind, a dense, chaotic, gravitationally violent neighborhood full of stars being pulled, stretched, and reshuffled by the unseen mass at its center. It's the kind of environment where, by most reasonable expectations, only the toughest, most solitary objects ought to survive for long. Which is exactly what makes the next discovery, announced 2 years after S4716, so difficult to square with that picture. Because the next discovery, announced 2 years later, found something in that same neighborhood that, by every existing model, simply shouldn't have been able to exist there at all. Binary stars, two stars locked in orbit around each other, like a slow-motion cosmic dance, are common throughout the universe. Estimates suggest a substantial fraction of all stars exist as part of binary or multiple star systems, with some surveys putting the figure for massive, sun-like and heavier stars at somewhere around half. In most regions of the galaxy, finding a binary is unremarkable. What had never been observed anywhere was a binary system surviving anywhere near a supermassive black hole. There was a good theoretical reason for that absence. A binary star system is a gravitationally delicate arrangement. The two stars are held together by their mutual gravity in a relatively gentle balance. Bring that pair close enough to an object as massive as Sagittarius A, and the black hole's own gravity starts competing with the gravity holding the pair together. The tidal forces involved, the same kind of stretching effect that, taken to the extreme, can shred a star entirely in what astronomers call a tidal disruption event, should, in theory, rip a loosely bound binary apart long before it ever got close enough to matter. For decades, that was the consensus. If binaries ever wandered near a black hole, they wouldn't last. In December 2024, an international team led by Florian Paesker, the same researcher behind the S4716 discovery, published a finding in the journal Nature Communications that overturned that assumption directly. Using years of spectroscopic data collected by the SINFONI instrument on the European Southern Observatory's Very Large Telescope, the team identified a binary star system, designated D9, orbiting inside the S cluster itself. The evidence wasn't a direct image. At that distance, the two stars are far too close together to be visually separated, even with the world's best telescopes. Instead, the discovery came from analyzing the system's light. As the two stars orbit each other, the wavelength of light coming from surrounding hydrogen gas oscillates rhythmically toward the red and then the blue, stretching and compressing as the stars swing through their mutual orbit. That periodic shift, tracked patiently across several years of observations, was the signature that gave the binary nature of D9 away. The system itself turned out to be remarkably young, somewhere around 2 to 3 million years old, barely a flicker of time on stellar timescales. The two component stars differ noticeably in mass. One carries roughly 3 times the mass of our Sun, the other about 3/4 of the Sun's mass. They orbit each other at a separation of around 238 million kilometers, completing one full mutual orbit approximately every 372 days, coincidentally, almost exactly the length of an Earth year, just describing two stars circling each other rather than a planet circling a star. And crucially, the entire system swings as close as roughly 6,000 astronomical units to Sagittarius A at its nearest approach, deep inside the same violent, tidally stressed neighborhood that, by the old models, should have torn it apart before it could even finish forming. Black holes are not as destructive as we thought, the study's lead author noted at the time the findings were announced, a striking statement, considering it came from someone studying the most destructive object known to physics. The discovery suggests that under the right conditions, a binary system can briefly survive, and possibly even fully form, in an environment astronomers had assumed was far too hostile to allow it. That survival looks to be temporary, though, based on the system's current trajectory. Researchers estimate that the gravitational influence of Sagittarius A will eventually win out. Within roughly 1 million years, simulations suggest the two stars in D9 are likely to merge into a single star, a slow-motion collision, driven by the relentless tidal pull of the black hole they're orbiting. D9 isn't a permanent resident of the S cluster. It's a temporary visitor caught mid-collapse, observed at almost exactly the right moment to be seen at all. And D9 wasn't alone. The same general region, the dense, chaotic S cluster, also turns out to host a population of strange dust-enshrouded objects called G-sources, things that behave gravitationally like stars, responding to orbital mechanics the way a compact object should, but that look in direct observation more like diffuse clouds of gas and dust than solid stars. The first of these, a cloud-like object called G2, was noticed as something unusual in the data as early as 2002 and confirmed to be on a collision course with the black hole's vicinity in 2012. Many astronomers expected it to be a simple, fragile cloud of gas, likely to be torn apart and consumed when it made its closest approach to Sagittarius A in 2014. That dramatic feeding event never came. G2 survived the encounter largely intact, behaving far more like a compact, star-like object wrapped in a shroud of gas and dust than like a simple cloud, leading the research team that tracked it to conclude it most likely conceals a dim, dust-shrouded young star at its core. Follow-up surveys later identified several more objects sharing the same strange profile, cataloging them collectively as G1 through G6. That single surprising survival was an early hint that the S cluster held more structural complexity than astronomers had assumed, a hint that the D9 discovery, a decade later, would confirm in a far more dramatic way. Their exact nature remains an open question. Some researchers suspect they may be binary stars in the process of merging, perhaps even a preview of what D9 itself will eventually become. Between S4716's record-breaking orbit and D9's improbable survival, a pattern starts to emerge. The region immediately surrounding Sagittarius A isn't simply chaotic and destructive. It's also somehow capable of hosting far more complex and fragile structures than anyone expected. Stars on migrating orbits, binary systems mid-collapse, mysterious dust-shrouded objects defying easy classification. The black hole's influence is real and extreme, but it isn't absolute. Things survive there, at least for a while, that theory said shouldn't be able to. It raises a fair question: if a star can migrate inward and settle into a 4-year orbit, and a fragile binary can hold together within a few thousand astronomical units of a black hole for millions of years, what else might be hiding in that same crowded, half-hostile neighborhood? Something with an even sharper, more useful signal than a star's orbit or a cloud of gas. That same tension, things existing where they shouldn't, signals appearing where none were expected, runs straight into the next discovery. And this one reaches even closer to Sagittarius A than S4716 or D9 ever have. For decades, one specific absence has nagged at astronomers studying the galactic center, separate from the question of winds and outflows we opened this video with. It's known, informally, as the missing pulsar problem. Here's the puzzle. A pulsar is the collapsed remnant of a massive star that ended its life in a supernova explosion, an incredibly dense, rapidly spinning neutron star, sweeping a beam of radio waves across space like a cosmic lighthouse as it rotates, sometimes hundreds of times per second. Given how densely packed the galactic center is with massive stars, and given how many of those stars should have already reached the ends of their lives and exploded, astronomers have long predicted that the region immediately around Sagittarius A ought to contain a substantial population of pulsars, potentially dozens hidden in the chaotic environment of the S cluster and the space surrounding it. But despite decades of dedicated searching, almost none have been found. As of recent surveys, astronomers know of only a handful of pulsars anywhere near the galactic center, roughly half a dozen confirmed examples, and even those sit comparatively far out, on the order of 100 to 130 light-years from Sagittarius A. Within the innermost light-year surrounding the black hole itself, the region where a pulsar's signal would be most scientifically valuable, only one confirmed exception exists: a highly magnetized neutron star called PSR J1745-2900, discovered in 2013 after an unexpected burst of X-rays drew telescopes to the region. It sits roughly a third of a light-year from Sagittarius A, spins once every 3 seconds, and carries one of the most extreme magnetic fields ever measured on any pulsar. It has proven useful precisely because of its location. Its signal passes directly through the turbulent gas surrounding the black hole on its way to Earth, letting astronomers use it as a kind of probe to measure the magnetic field of that surrounding material. But useful as it's been, a single magnetar sitting a third of a light-year out doesn't come close to solving the deeper puzzle. Astronomers don't just want any pulsar near the galactic center. They want one close enough and in a tight enough orbit to directly map the gravity of Sagittarius A itself. That absence matters enormously because a confirmed pulsar in a tight orbit around Sagittarius A would be one of the most valuable scientific instruments astronomers could ask for. Pulsars function as extraordinarily precise natural clocks. Track the timing of a pulsar's radio pulses as it swings close to a supermassive black hole, and you can measure exactly how spacetime bends and drags around that black hole, testing Einstein's general relativity under conditions no laboratory on Earth could ever reproduce. As a pulse of radio waves passes close to an object as massive as Sagittarius A, general relativity predicts the pulse should be measurably bent and delayed by the surrounding curved spacetime, a subtle effect, but one precise enough timing could detect and measure directly. It's the kind of measurement that could confirm or challenge our understanding of gravity itself in its most extreme known setting, and potentially even reveal whether the central object is spinning, and if so, how fast, a property current evidence still can't fully pin down. In early 2026, a research team working with the Breakthrough Listen Initiative, an organization better known for searching for signs of extraterrestrial technology, but which also conducts some of the most sensitive pulsar surveys ever performed, announced a potentially significant step toward closing that gap. Led by Columbia University researcher Karen Perez, the team conducted one of the deepest pulsar searches ever directed at the galactic center, using the Green Bank telescope in West Virginia. Part of why this search differed from decades of earlier attempts comes down to a specific technical obstacle: scattering. The space between Earth and the galactic center isn't empty. It's filled with a turbulent sea of ionized gas, and as radio waves pass through that gas on their way to us, they get smeared and delayed in ways that can blur a pulsar's normally crisp, regular pulses into an undetectable haze. That scattering effect grows weaker at higher radio frequencies, roughly in proportion to the fourth power of the frequency used, meaning that simply doubling the observing frequency can reduce the smearing by a factor of around 16. Perez and her collaborators deliberately observed at high frequencies, between 8 and 12 gigahertz, specifically to cut through that obscuring gas as effectively as current technology allows. Among thousands of signal candidates sifted from the data, one stood out: a possible millisecond pulsar, spinning at a rate of once every 8 milliseconds, detected persistently across roughly an hour of observation. The team has informally nicknamed it the Breakthrough Listen Pulsar, or BLPSR. It's important to be precise about what this is and what it isn't. This is not a confirmed pulsar. It's a single, promising candidate identified in one survey that has not yet been independently redetected or fully confirmed through follow-up observation. The research team itself describes it that way, an intriguing signal warranting serious further investigation, not a settled discovery. Given how sensitive the survey was, the researchers note they should have been capable of detecting roughly 10% of the millisecond pulsars and around half of the slower, more conventional pulsars that current models predict should exist in that region, And yet across all of that sensitivity, this single candidate was the only one that turned up. That itself deepens the missing pulsar puzzle rather than resolving it. Either the predicted population simply isn't there in the numbers theory expects, or something about the extreme environment around Sagittarius A is actively hiding or destroying a population that should otherwise be detectable if the candidate is eventually confirmed. And if follow-up observations show it sits in a sufficiently tight orbit around Sagittarius A, ideally a year or less, the scientific payoff would be enormous. A natural laboratory for testing general relativity in the strongest gravitational field, accessible to direct observation anywhere in the galaxy. For now, though, it remains exactly what its name implies: a candidate, not a confirmation, and a small but telling piece of evidence that the immediate environment around Sagittarius A keeps producing exactly the kind of borderline, almost impossible signals that have defined this black hole story from the beginning. Stars that shouldn't be able to form where they're found, binaries that shouldn't be able to survive where they're found. Now, possibly, a pulsar nobody expected to detect at all, sitting closer to Sagittarius A than any other has been found before. Which brings us to the most serious challenge yet, not to a detail about Sagittarius A**S environment, but to its fundamental identity. By the early 2020s, as we covered earlier in this video, the case for Sagittarius A being a genuine supermassive black hole looked about as solid as evidence in astrophysics gets. Stellar orbits matched the predicted mass. Gravitational redshift matched Einstein's equations. The Event Horizon Telescope had even produced a photographed shadow, with a size and shape matching theoretical predictions almost exactly. In February 2026, a team of researchers led by astrophysicist Valentina Crespi of the Institute of Astrophysics La Plata published a study in the monthly notices of the Royal Astronomical Society that reopened a question most of the field considered closed. What if it isn't a black hole at all? The proposal isn't a vague suggestion. It's a fully worked physical model, and the underlying physics, while exotic in application, rests on a genuinely simple principle. Fermions are a broad category of subatomic particles, the category that includes the electrons and neutrons making up ordinary matter, that obey a rule called the Pauli exclusion principle, which prevents two identical fermions from ever occupying exactly the same quantum state in the same place. In practice, that rule acts like a kind of quantum pressure, resisting compression past a certain point, the same basic effect that keeps the collapsed core of a dead star from compressing indefinitely into a black hole in some stellar collapse scenarios. Crespi's team proposes that a hypothetical, much lighter species of fermion, a candidate for dark matter, the invisible mass known to outweigh ordinary matter across the universe, but never yet directly detected, could under the right conditions settle into two connected structures, an extraordinarily dense compact central core surrounded by a much larger, far more diffuse outer halo, with the core and halo behaving in effect as two expressions of the same underlying substance, rather than as a black hole sitting inside a separate halo of ordinary dark matter. What makes this proposal more than just an interesting thought experiment is how directly it engages with the actual observational evidence. The model isn't simply trying to explain away the stellar orbits in the S cluster. It's built specifically to reproduce them alongside other independent observations, including the broader rotational behavior of stars much farther out in the galaxy, drawing on recent data from the European Space Agency's Gaia mission, which has spent years precisely mapping the positions and motions of well over 1 billion stars across the Milky Way. That's a meaningful distinction from many previous alternative models, which tended to focus narrowly on just the innermost stars. According to the research team, their model successfully reproduces the observed orbit of S2 with a level of precision nearly indistinguishable from the standard black hole model. It also accounts for the strange, dust-shrouded G-sources we mentioned earlier in the same cluster that hosts S4716 and D9. Most strikingly, the proposal directly confronts the single piece of evidence that seemed, on the surface, to settle the question for good: the 2022 Event Horizon Telescope image, a separate. Earlier study by some of the same researchers had already demonstrated mathematically that a sufficiently dense and compact dark matter core, illuminated by the same hot, glowing gas that surrounds Sagittarius A in the standard picture, would bend light strongly enough to cast a shadow nearly identical in appearance to the one the EHT actually photographed, a bright ring encircling a dark central region. Not because light is crossing an event horizon and vanishing forever, but because it's being bent by sufficiently concentrated gravity to produce something that looks, from any practical observational standpoint, the same. It's worth being completely clear about where this leaves things, because this is exactly the kind of claim that's easy to sensationalize and important to present accurately. The researchers behind this study are not claiming to have disproven the black hole model. They are not claiming their model is the better explanation. What they've shown by their own account is that current observational data cannot yet statistically distinguish between the two scenarios, that a black hole and a sufficiently exotic dark matter core would with present instruments look and behave close enough to identically that we can't yet rule either one out with confidence. As the research team put it in their own conclusions, meaningfully better data and measurement precision will be required before the question can be settled either way. There is, encouragingly, a theoretical difference between the two models that future observations might eventually be able to detect. General relativity predicts that light passing close enough to a true black hole's event horizon should display a specific signature called a photon ring, a kind of gravitational echo, produced only because there's an actual point of no return for light to circle around before escaping or vanishing. A dark matter core, lacking an event horizon altogether, shouldn't produce that same signature in the same way. One research group has previously claimed to detect hints of exactly this kind of photon ring around Sagittarius A in existing data, but that specific claim has faced significant pushback and criticism from other scientists in the field and remains very much unresolved itself. So here is where this video's central open question now stands, fully assembled. For 50 years, Sagittarius A behaved like an exception to every rule governing supermassive black holes, quiet, dim, with no detectable outflow, sitting at the center of a chaotic stellar neighborhood that kept producing objects that, by the old rules, shouldn't have been able to exist there at all. And now, a serious, peer-reviewed alternative model suggests the explanation for at least some of that strangeness might be that we've been looking at the wrong kind of object from the very beginning. It's worth sitting with how unusual it is for a question like this to still be open. Most of modern astrophysics doesn't work this way. The vast majority of objects astronomers study have been narrowed down to a single, well-supported explanation, with competing alternatives ruled out decades ago. Sagittarius A is one of a small handful of objects close enough and well-observed enough for a fundamental question about its basic nature to remain genuinely, scientifically unresolved in the present day. That's not a flaw in the science. It's a sign of exactly how strange and extreme this particular object is, sitting at the center of the one galaxy we can study in this kind of detail. We are not going to leave that question hanging indefinitely. In the next part of this video, we'll return to it directly, alongside the discoveries that finally explain why Sagittarius A spent 50 years looking so deceptively calm in the first place. Because while astronomers were debating what Sagittarius A might be, 3 separate teams were independently uncovering evidence about what it actually did in the relatively recent past. And what they found suggests quiet was never the right word at all. We opened this video with a promise about a 50-year search finally answered, and a black hole whose past turns out to be far louder than its present. It's time to deliver on that promise, and the first piece of evidence didn't come from studying Sagittarius A directly at all. It came from studying its neighbors. Scattered across the region surrounding the galactic center are enormous, slow-drifting clouds of molecular gas, vast, cold reservoirs of raw material, some of them light years across, left over from the same processes that built the galaxy itself. Astronomers have studied these clouds for decades, mostly as background structure, context for whatever was happening closer to the black hole. In January 2026, one of them turned out to be hiding something extraordinary. The discovery came from a space telescope called XRISM, the X-ray Imaging and Spectroscopy Mission, a joint project between the Japanese space agency JAXA and NASA, launched in 2023. XRISM's defining advantage isn't raw sensitivity, it's precision. The instrument can resolve the energy of incoming X-ray photons with extraordinary fineness, capable, as one researcher put it, of distinguishing 1 part in 1,000, the equivalent of upgrading from a blurry photograph to a sharp, high-resolution image of the exact same scene. That kind of precision matters enormously for a discovery like this one. Earlier generations of X-ray telescopes could detect that a molecular cloud near the galactic center was glowing in X-rays and could make a reasonable case for why. But distinguishing between 2 subtly different physical processes producing that glow, cosmic rays striking the gas directly, versus reflected light from a distant flare, requires measuring the exact shape and energy of individual spectral lines with a level of detail that older instruments simply couldn't deliver. XRISM was purpose-built to close exactly that kind of gap, and the Sagittarius A result became one of its first major demonstrations of what that improved precision could actually accomplish. A research team led by Stephen Dye Kirby, an astronomer at Michigan State University, pointed XRISM at one of these molecular clouds near the galactic center and zoomed in on 2 extremely narrow X-ray emission lines in its spectrum, signatures associated with iron atoms embedded in the cloud's gas. There were 2 competing explanations on the table for why this cloud was glowing in X-rays at all. One possibility was that high-energy cosmic ray particles zipping through the cloud were exciting the gas directly. The other was something stranger, that the cloud wasn't producing its own glow at all, but reflecting light. Specifically, reflecting an X-ray outburst that had originally come from Sagittarius A itself. Sometime in the past, light bouncing off the cloud the way moonlight is really just reflected sunlight, arriving at our telescopes only after taking a longer, indirect path to get here. XRISM's precision was sharp enough to settle the question. The exact energies and shapes of those iron emission lines, measured with a clarity no previous telescope could achieve, ruled out the cosmic ray explanation outright. The evidence pointed unambiguously to reflection. This cloud is, in effect, a mirror, and what it's reflecting is a powerful X-ray flare that once blazed out from Sagittarius A. Here's where the discovery turns into something closer to detective work than ordinary observation. Because the cloud doesn't sit at the same location as the black hole, light reflecting off, it has to travel a slightly longer path to reach Earth than light traveling directly from Sagittarius A itself would. That extra path length translates into a time delay, meaning the reflected light we're seeing now, in 2026, is showing us an event that, from Sagittarius A's own perspective, actually happened earlier. Based on the geometry of the cloud and the timing of the signal, the research team determined that the flare occurred somewhere between a few hundred and about 1,000 years before the light we're now observing was emitted. It's a similar principle to how sound echoes work in a canyon, just stretched across light years instead of meters. Shout once, directly at a friend standing nearby, and they hear you almost instantly. Shout the same sound toward a distant canyon wall, and the echo that bounces back arrives later, delayed by exactly however much farther that reflected sound had to travel. Substitute X-ray flare for shout and molecular cloud for canyon wall, and you have in essence exactly what XRISM detected, just operating on a timescale of centuries rather than seconds. There's a layer of cosmic irony buried in that timeline, worth sitting with for a moment. Sagittarius A sits roughly 26,000 light-years away, which means any light it produces takes 26,000 years to reach Earth, full stop, regardless of which path it takes. The direct light from this particular flare, the light that traveled straight from the black hole to us, without bouncing off anything, would have already swept past Earth a very long time ago, arriving and departing, unnoticed almost certainly before any instrument on this planet existed capable of detecting it. What we're catching now is only the echo, the same flare's light, delayed by an extra few hundred to 1,000 years because of the longer, indirect path it had to take by bouncing off the cloud first. We didn't miss the flare. We're catching its afterimage, fashionably late, because geometry gave us a second chance the original signal never offered, and the flare itself was not subtle. According to the research team's analysis, during this outburst, Sagittarius A was shining roughly 10,000 times brighter in X-rays than it appears today. That kind of brightness in the standard picture of how supermassive black holes work points to one specific cause: a substantial episode of active feeding, with significantly more gas falling toward the black hole than is falling in now. For that brief window, brief on a cosmic timescale, though it likely lasted years or decades from a human perspective, Sagittarius A wasn't behaving like the dim, sleepy object we've spent the past 2 parts of this video describing. It was behaving like exactly the kind of actively accreting black hole astronomers expect to see at the centers of more typical galaxies. "I wasn't prepared for this," Di Kirby said when describing the finding. "It's a fair reaction." After 50 years of studying Sagittarius A as the quiet exception to every rule governing supermassive black holes, the evidence finally arrived to suggest the exception might not be permanent at all, just a temporary lull. Caught between flares that this object has clearly been capable of producing all along, it's worth resisting one tempting but inaccurate way to picture this discovery. A flare occurring a few hundred to 1,000 years ago might suggest some medieval astronomer somewhere could, in principle, have looked up and witnessed it. That's not how this works. X-rays don't penetrate Earth's atmosphere. No observer on the ground in any century could have detected this event directly, no matter how dramatic it was. And the flare itself wasn't even visible light in the first place. It was high-energy radiation, invisible to the naked eye under any circumstances, requiring a space-based X-ray telescope, something that's existed for less than a single human lifetime, to detect at all. The flare happened. It was real and it was dramatic, but it left no trace anyone on Earth could have noticed at the time. We are the first beings, as far as we know, to ever become aware that it happened at all, and only because a cloud of gas, light years away, happened to be positioned to catch the light and bounce it back toward us, delayed centuries later. The XRISM result wasn't an isolated curiosity. It fits into a body of research stretching back over a decade, all built around the same basic idea, that the molecular clouds surrounding Sagittarius A function collectively as a kind of distributed archive, each one capable of preserving a slightly different snapshot of the black hole's past activity depending on its distance and position relative to the center. Earlier studies using X-ray observatories like Chandra and Suzaku had already found hints of this same phenomenon in other nearby clouds, including a large complex called Sagittarius C, situated at a different position and distance from the black hole than the cloud XRISM examined. Astronomers studying Sagittarius C used a similar reflection-based technique, examining how the region's X-ray brightness varied across different epochs of observation, sometimes spanning more than a decade of repeated study with the same instruments. Those studies pieced together evidence suggesting Sagittarius A had experienced periods of significantly elevated activity stretching back roughly 500 years. With the black hole's average X-ray output during some of those active stretches running 4 to 6 orders of magnitude, that's somewhere between 10,000 and 1,000,000 times brighter than its current quiet baseline. Some of that earlier evidence even pointed to multiple distinct flaring episodes, rather than one single outburst, layered on top of a longer-term elevated state, including at least 2 shorter flares lasting roughly 5 to 10 years apiece, embedded within that longer 5-century stretch of heightened activity. What made the 2026 XRISM result so significant wasn't that it discovered the basic concept of light echoes for the first time. It was the precision, where earlier instruments could detect that a cloud was glowing unusually and make a rough case for reflection over direct emission. XRISM's superior energy resolution allowed Dai Kirby's team to confirm the reflection hypothesis with a level of confidence that ruled out the competing explanation almost entirely, turning a plausible interpretation into a measured result. Think of it as the difference between hearing a vague rumor about a historical event from multiple second-hand sources versus finding a single, precisely dated written record. The earlier studies gave astronomers good reason to suspect Sagittarius A hadn't always been quiet. XRISM gave them a specific, well-measured data point confirming it, and there's a broader implication buried in this technique that goes beyond just Sagittarius A specifically. Because different molecular clouds sit at different distances and positions relative to the black hole, each one reflects the same historical flares with a slightly different time delay. In principle, by patiently studying enough clouds across the galactic center, astronomers can reconstruct an actual timeline of Sagittarius A's past activity, not just confirming that flares happened, but mapping out roughly when and how bright and how often. One of the scientists involved in this line of research compared it to using delayed echoes to map out the shape of a cave from the outside, using only the way sound bounces back to you. It's a genuinely clever piece of astronomical detective work, turning passive clouds of gas into an unintentional historical recording device, decades or centuries after the events they captured actually happened. Extend that idea far enough, and the molecular clouds scattered across the galactic center start to resemble something closer to a scattered archive than a simple gas reservoir. Dozens of independent, imperfect witnesses, each holding a fragment of the same story recorded at a different moment and from a different angle. Waiting for an instrument precise enough to read them. XRISM's contribution to this particular cloud is, by the team's own framing, a first proof of concept rather than a finished history. Future observations, targeting additional clouds at different distances, could in principle extend that timeline further back, filling in gaps between the roughly 500-year history already sketched out by earlier Chandra and Suzaku studies, and the more precisely dated flare XRISM has now pinned down. This reframes the entire question this video has been building toward. It's not simply that Sagittarius A might have flared once, 1,000 years ago, in an isolated, unexplained event. The growing body of evidence increasingly suggests a black hole with a genuinely active, variable history, quiet for long stretches, but punctuated by real episodes of significant feeding and brightening, behaving, when the gas supply allows it, much more like its more dramatic supermassive cousins elsewhere in the universe. Which raises an obvious question. If Sagittarius A really has been feeding heavily within the last 1,000 years or so, sometimes 10,000 times brighter than its current state, where did all of that excess energy and material actually go? An actively feeding black hole, by the same standard physics we discussed back in part 1, shouldn't just brighten and absorb material quietly. It should be pushing some of that material back outward, in exactly the kind of wind that decades of searching had failed to find. That's exactly the question a separate research team, working with a completely different set of instruments, set out to answer. And in June of this year, they found something. We told you at the very start of this video that the 50-year search for Sagittarius A's missing wind had finally ended. Here's how. The team behind the discovery, based at Northwestern University and led by astronomer Mark Gorski, alongside fellow researcher Leah Merchikova, approached the problem with an enormous amount of patience. Rather than searching for the wind directly, which had failed for decades, they focused instead on mapping its likely consequences, specifically the cold molecular gas that fills the space within a few light-years of Sagittarius A. The same kind of gas that makes up the reflective clouds we just discussed in the previous chapter. Using the Atacama Large Millimeter/Submillimeter Array, or ALMA, in Chile, the team assembled nearly 5 years' worth of observations, tracking emission from carbon monoxide molecules, a standard, reliable tracer astronomers use to map cold molecular gas within roughly 1 parsec, or about 3 light-years, of the black hole. ALMA itself should sound familiar. It's one of the very telescopes that contributed to the Event Horizon Telescope network back in part 1, the same array of high-altitude dishes in the Chilean desert that helped produce the 2022 shadow image. Here, though, the team used it for an entirely different purpose, not resolving the extreme, rapidly flickering environment right at the black hole's edge, but instead patiently mapping the much cooler, gentler glow of molecular gas spread across several light-years around it. This wasn't a quick or simple observation. Sagittarius A itself produces a bright, rapidly flickering glow at radio wavelengths, and that glow can easily wash out or contaminate the kind of faint, fine structure the team was hoping to detect in the surrounding gas. A significant part of the project involved carefully modeling and subtracting Sagittarius A's own variable emission from the data. Isolating the much fainter signal from the gas around it, a painstaking process that helps explain why a signature theory had predicted for 50 years took this long to actually confirm. What remained once that painstaking subtraction was complete was a feature nobody had been able to see clearly before, a broad cone-shaped cavity carved directly out of the cold molecular gas, roughly 3 light-years long, opening outward, at an angle of about 45 degrees, pointing directly back towards Sagittarius A at its narrow end. A hollow, conical gap, sitting exactly where decades of theory had predicted an outflow should be, but where decades of searching had never managed to actually find one. To confirm what was causing that empty cavity, the team turned to a second instrument, NASA's Chandra X-ray Observatory. If the gap in the cold gas really was being carved out by a hot wind blowing from the black hole, that wind itself should show up as hot, X-ray emitting material filling the same cavity. That's exactly what Chandra's data showed. The cone-shaped gap in the cold gas was filled with hot, X-ray bright material, lining up with the ALMA structure with enough precision to leave little doubt about the connection. In the composite image the team eventually released, the two datasets are color-coded together. The cold gas mapped by ALMA, rendered in orange, tracing broken clumpy arcs that nearly encircle the black hole, but break open precisely where the cavity sits, and the hot gas detected by Chandra, rendered in blue, glowing exactly inside that gap. Like a wedge of fire cut into a ring of frozen material. Merchikova later described her own reaction to seeing the two datasets overlap for the first time. The instinct, she said, wasn't celebration, but suspicion, the immediate worry that something must be wrong with the analysis. It was only once the X-ray data slotted neatly into place against the radio map that the results started to feel real. The research team also went out of their way to rule out other possible explanations for the cavity, the combined winds of multiple nearby stars, for instance, or the aftermath of a relatively recent supernova explosion somewhere in the vicinity. Stellar winds from the cluster of massive stars near Sagittarius A are real and do shape some of the surrounding gas, but they don't naturally produce a single narrow, sharply cone-shaped gap pointed precisely back at the black hole. A collection of stars scattered across the cluster would be expected to carve out a messier, more diffuse pattern, not one tidy cone, with its apex at Sagittarius A itself. A past supernova was considered too, since exploding stars are certainly capable of clearing out pockets of gas. But the energy budget and the specific geometry of the cavity didn't fit that scenario nearly as well as they fit a wind launched directly from the black hole. The shape, scale, and energy needs of the cavity, the team concluded, pointed back to one specific source: a hot, energetic wind launched from Sagittarius A itself, persistent enough to have been actively sculpting the surrounding gas for at least the past 20,000 years. It's worth being precise about the scale of what was found, because this isn't a story about Sagittarius A suddenly transforming into a different kind of object. Compared to the powerful winds and jets seen blasting away from actively feeding black holes at the centers of other, more energetic galaxies, the wind from Sagittarius A is, by the research team's own description, relatively modest, not an impressive fire hose so much as a persistent, gentle exhale. As Gorski put it plainly, while describing the motivation behind the years-long search, unless a black hole exists in a perfect vacuum, it has to produce some kind of wind somehow. Physically, there was never a real way around it. The genuine surprise was never that Sagittarius A might be capable of this. It was that after 50 years of trying, nobody had been sensitive enough to actually catch it doing so, until ALMA's years of patient, carefully processed observation finally revealed a faint signature that had been there all along. As one astrophysicist not involved in the study, Priyamvada Natarajan of Princeton, put it when commenting on the result, Sagittarius A has long been the great frustration of galactic center astrophysics, close enough to study in extraordinary detail, yet stubbornly quiet, apparently windless. This result, in her words, dismantles that picture entirely. It's a fitting way to describe a discovery that took half a century of failed searches to arrive at, and ultimately came down to nothing more exotic than better instruments, more patient data collection, and the willingness to keep looking for something everyone agreed should be there. Step back now and look at everything this video has assembled so far, because the pieces are finally ready to be placed next to each other. For 50 years, Sagittarius A presented astronomers with a contradiction. Every confirmed measurement, the stellar orbits, the gravitational redshift, the photographed shadow, the magnetic field structure, pointed to a textbook supermassive black hole, identical in fundamental nature to the much more dramatic, much brighter examples found at the centers of other galaxies. And yet, in its observed behavior, it refused to act like one. No strong outflow, no dramatic luminosity. A black hole that, by every visible measure, looked like it was barely doing anything at all. We now have a far more complete answer for why. Within roughly the last 1,000 years, and quite possibly more than once, Sagittarius A underwent a genuine outburst, a period of significantly increased feeding, during which it shone some 10,000 times brighter in X-rays than it does today. Vividly recorded as a delayed light echo in at least one nearby molecular cloud, with earlier studies hinting at a broader centuries-long history of similar episodes recorded across several other clouds nearby, and independently using a completely different set of instruments and observational techniques. A second research team has now confirmed that Sagittarius A is in fact producing the kind of wind theory always said an actively feeding black hole should produce, a faint but genuine outflow carving a measurable cavity into the surrounding gas, sustained for at least the past 20 years. Put those two results together, and the picture of Sagittarius A shifts substantially. This was never simply a uniquely calm black hole, somehow exempt from the rules governing every other supermassive black hole astronomers have studied. It's a black hole whose activity varies dramatically over time, capable of dramatic flares and sustained winds, just like its more famous cousins elsewhere in the universe, but currently caught by pure observational chance during one of its quieter intervals. The 50-year absence of evidence was never proof that Sagittarius A was fundamentally different. It was a measure of how difficult it is to detect a faint signal from an object that happens to be passing through a quiet phase, observed from 26,000 light-years away, through a turbulent, obscuring galaxy in between. Consider, too, what this does to the picture we built back in Part 1, when we described Sagittarius A as ranking among the dimmest supermassive black holes ever measured. A nightlight, we said, compared to the furnace its mass theoretically allows. That comparison still holds for the object's average behavior over the short window we've been able to observe it, but it no longer captures the full picture. A nightlight that occasionally flares 10,000 times brighter, then dims back down over centuries, isn't behaving like a permanently underpowered version of an active black hole. It's behaving like an active black hole caught, almost arbitrarily, between meals. There's a genuinely humbling lesson buried in that timeline, worth sitting with before we move on. Every observation discussed across this entire video, the stellar orbits, the 2022 image, the magnetic fields S4716, D9, the pulsar candidate, the flare, the wind, represents at most a single snapshot drawn from a black hole whose activity plays out over timescales of centuries and millennia. We have been studying Sagittarius A in meaningful detail for barely 50 years, against an object whose behavior apparently shifts meaningfully on 1,000-year timescales. 50 years isn't even the blink of an eye. It's closer to a single, isolated frame, pulled from a film stretching back far longer than we've had the instruments capable of watching it. It also reframes something we said earlier in this video, back when we first laid out the puzzle of Sagittarius A's apparent dimness. We described the leading explanation at the time as simple starvation, less fuel falling in, less radiation coming out. That explanation isn't wrong exactly, it's incomplete. The fuel supply around Sagittarius A isn't a fixed, steady trickle. It's variable, rising and falling over time as gas clouds drift inward, get disrupted, or get swept away by the very wind the black hole itself produces. Quiet was never a fixed property of this object, the way mass or distance are fixed properties. It was a phase, a long one by human standards. But a phase nonetheless, bookended by flares we're only now learning how to detect, fading in and out of view depending on how much material happens to be available to feed on at any given moment. Which brings us finally back to the question we deliberately left open at the end of the last part of this video. Everything we've just described, the flare, the wind, the gas cavity, the centuries of varying activity, was built on the assumption that Sagittarius A is, in fact, a black hole in the traditional sense, with genuine accretion, genuine feeding, and a genuine event horizon producing all of this observed behavior. But we also told you about a serious, peer-reviewed alternative, the possibility that the object at the center of our galaxy isn't a black hole at all, but an extraordinarily dense core of fermionic dark matter, mimicking a black hole's gravity closely enough to explain the same stellar orbits and even reproduce the same photographed shadow. So does the discovery of a real flare and a real wind settle that question? Does it tip the scale firmly back toward the black hole explanation? That's exactly where we're headed next, along with one final piece of context that puts everything in this video into perspective. What any of this actually means for an object that every single one of us has been quietly orbiting this entire time without ever feeling a thing. We left the question open deliberately back at the end of part 2. Is the object at the center of our galaxy a genuine black hole, or could it be something stranger, an extraordinarily dense core of fermionic dark matter, mimicking a black hole's gravity closely enough to fool nearly every measurement we've thrown at it? It's time to weigh what we actually have. This isn't a question with an obvious, predetermined answer, and it's worth being honest about that rather than rushing toward a tidy conclusion just because one exists. Throughout the history of physics, obviously correct explanations have occasionally turned out to be wrong, and fringe alternatives have occasionally turned out to be right, often because somebody was willing to keep testing an idea seriously long after most of the field assumed the matter was settled. The Crespi-Teams model deserves to be weighed on its actual merits, not dismissed simply because it challenges 50 years of accumulated assumption. Start with what the dark matter model can explain. According to its own authors, it reproduces the orbit of S2 with a precision nearly matching the standard black hole model. It accounts for the broader rotation of stars out in the galaxy's disk, using the same underlying mathematics, a notable strength, since many earlier alternative models tended to focus narrowly on the orbits closest to Sagittarius A, without successfully connecting to the galaxy's much larger-scale structure. It even reproduces something that once seemed like the strongest possible confirmation of a true event horizon, the 2022 Event Horizon Telescope image. A sufficiently dense, compact core of this exotic material, illuminated by the same glowing gas that surrounds Sagittarius A in the conventional picture, bends light strongly enough to cast a shadow nearly indistinguishable from the one astronomers actually photographed. That's a genuinely serious model. It isn't a fringe idea dismissed by the field. It's a peer-reviewed, mathematically worked proposal, built specifically to engage with the real data, by researchers taking the alternative seriously enough to test it rigorously against observation, rather than simply asserting it as a possibility and leaving the comparison to others. Now weigh that against the broader body of evidence this video has covered. In 2018, years before the EHT image existed, the gravity instrument on the Very Large Telescope tracked 3 bright flares of infrared light, orbiting Sagittarius A at roughly 30% of the speed of light. These flares weren't random flickers. Their position, tracked precisely enough to detect a subtle, repeating wobble, traced out small loops, the signature of hot, glowing material genuinely circling something, rather than simply flickering in place. The motion of those flares matched, with notable precision, the predicted behavior of hot, glowing material circling at the innermost stable orbit, the closest distance an object can stably orbit a black hole before gravity inevitably pulls it past the point of no return. It was, in effect, the first time astronomers had watched matter trace out the curvature of spacetime at the very edge of where stable orbits become possible at all. That specific concept, the innermost stable orbit, isn't just a generic feature of anything sufficiently massive and compact. It's a structural prediction tied specifically to the existence of an event horizon, baked into the geometry of spacetime, immediately surrounding a true black hole, the mathematical consequence of gravity becoming so extreme that past a certain boundary, no stable circular orbit can exist at all. A diffuse, extended core of dark matter, however dense at its center, doesn't naturally produce that same sharp boundary in the same way, since it lacks the single, true point of no return that gives rise to it. Then add the flares and the wind we just spent the last part of this video describing, an object whose brightness can spike 10,000-fold over a span of years to decades. Then fade back down over centuries, and one that's continuously launching a measurable outflow of hot gas, is behaving exactly the way standard accretion physics says a black hole should behave as it intermittently feeds on infalling material near an event horizon. None of this strictly proves the dark matter model wrong. A sufficiently exotic, dynamic configuration of compact matter might, in principle, be engineered to reproduce similar variability too. But every additional piece of dynamic, time-varying behavior we observe is one more thing the alternative model has to separately account for, on top of the static orbits and the shadow it was originally built to explain. So where does that leave the actual scientific consensus? Largely where it was before any of this year's discoveries, leaning heavily, but not completely irreversibly, toward the conventional black hole explanation. The researchers behind the dark matter proposal have been explicit and admirably careful about this themselves, in their own published conclusions. They state plainly that current data cannot yet statistically distinguish with full confidence between their model and the standard black hole picture, and that meaningfully better data and measurement precision will be required before the question can be considered settled one way or the other. There is, fortunately, a path toward an answer that doesn't rely on accumulating more circumstantial behavioral evidence. We mentioned it briefly back in Part 2, the photon ring. General relativity predicts that light passing close enough to a true event horizon should produce a specific faint signature, a kind of gravitational echo, a thin secondary ring of light produced only because there's an actual one-way boundary for light to circle around before either escaping or being lost forever. The mechanism is almost poetic, light that gets caught in a tight, unstable loop around the black hole, circling once or even multiple times before finally breaking free, and continuing on toward our telescopes, arriving slightly displaced and dimmer than the main glow, like a faint copy nested just inside the bright ring the EHT already photographed. A dark matter core, lacking an event horizon by definition, shouldn't produce that exact same signature in the same way. One research group has previously claimed hints of detecting exactly this kind of photon ring around Sagittarius A in existing data, though that specific claim faced significant pushback from other scientists and remains unresolved. The signal involved, if it's real at all, is extraordinarily faint, orders of magnitude dimmer than the main ring structure, sitting right at the edge of what current instruments can reliably distinguish from noise. Detecting it conclusively will likely require the next generation of instruments, upgrades like Gravity Plus, already being deployed on the Very Large Telescope to substantially boost its sensitivity to exactly this kind of faint close-in signal, and entirely new facilities like the Extremely Large Telescope's METIS instrument and the planned Square Kilometer array, both still under construction. None of these instruments are likely to deliver a definitive answer within the next year or two. Realistically, this is a question that will probably take the better part of another decade to settle conclusively. As each new facility comes online and adds its own layer of precision to the existing data. Until one of those facilities delivers a clean, confirmed detection, the honest answer is that the case for a conventional black hole is strong, well supported by decades of converging evidence, and still, technically, not airtight. It's worth pausing on why this particular open question is worth caring about, beyond simple curiosity about one object at the center of our own galaxy. The stakes reach considerably further than Sagittarius A itself. Start with dark matter. Astronomers have known for decades, with overwhelming confidence, that some form of unseen mass dominates the universe's total gravitational budget, outweighing all the stars, planets, gas, and dust combined by a wide margin. We know it's there because of exactly the kind of evidence the Crespi team's own model draws on. The way galaxies rotate, the way light bends around galaxy clusters, the way the universe's large-scale structure assembled itself over billions of years. What dark matter actually is, at a fundamental particle level, remains one of the largest unsolved problems in all of physics. Decades of dedicated experiments built specifically to directly detect dark matter particles interacting with ordinary matter here on Earth, enormous ultrasensitive detectors buried deep underground. Shielded from the cosmic radiation that would otherwise drown out a genuine signal, have so far come up empty, finding no confirmed direct detection of a dark matter particle anywhere. If even a portion of the dark matter permeating our galaxy is capable of clumping into something as extraordinarily dense and structured as a black hole mimicking core, that would represent a genuinely new clue about the particle physics underlying it, arguably one of the most significant indirect dark matter detections ever made, hiding in plain sight at the center of our own galaxy this entire time. Now consider the flip side. If Sagittarius A turns out to be a conventional black hole after all, which to be clear remains by far the better supported outcome given everything covered in this video, that confirmation still matters enormously because Sagittarius A functions as the closest, best studied example of an entire class of objects astronomers now believe sits at the center of nearly every sufficiently large galaxy in the universe, including the most distant, earliest galaxies, observed by instruments like the James Webb Space Telescope. We mentioned back in Part 1 that nobody has fully explained how some of the universe's supermassive black holes grew so enormous, so early in cosmic history, a puzzle that's only deepened as JWST has continued spotting massive black hole candidates in galaxies from the universe's first billion years. Sagittarius A, sitting close enough for this level of direct study, offers one of the only real testing grounds for the detailed physics, accretion rates, feeding episodes, outflow behavior, that any complete theory of supermassive black hole growth eventually has to get right. It also offers a useful point of comparison against the only other black hole humanity has photographed directly. M87, the supermassive black hole at the center of the galaxy Messier 87, roughly 1/500 times more massive than Sagittarius A and far more energetically active. Complete with a dramatic jet of particles blasting outward at near light speed across thousands of light years. M87 behaves like the loud end of the supermassive black hole spectrum. Sagittarius A, even accounting for its newly discovered flares and wind, remains much closer to the quiet end, having confirmed detailed case studies at both ends of that spectrum. 1,1 dramatic, both imaged with the same instrument and measured against the same underlying physics, gives astronomers a far richer foundation for understanding the full range of behavior these objects are capable of. Rather than generalizing from a single example, that's the real reason this question hasn't been allowed to simply rest on probably a black hole, case closed. 26,000 light-years away sits the only supermassive black hole humanity will likely ever be able to study at this level of detail, in our lifetimes or for a long while after. Getting the answer right, rather than just getting a plausible-sounding answer, is worth the additional decades of instrument building it might take. Sagittarius A sits roughly 26,000 light-years from Earth, containing the mass of about 4 million suns, compressed into a region smaller than the orbit of Mercury. It was first detected indirectly as a radio source in 1974 and only confirmed as a genuine compact, supermassive object decades later through the patient tracking of orbiting stars, work recognized by the 2020 Nobel Prize in Physics. In 2022, it became the second black hole ever directly photographed, its shadow matching general relativity's predictions with remarkable precision. And in 2024, a follow-up image revealed strong, organized magnetic fields spiraling at its very edge. Surrounding it is one of the strangest stellar neighborhoods in the galaxy, a dense cluster of stars on extreme tightly wound orbits, including objects that shouldn't by older models be able to exist there at all, a star with a 4-year orbital period, reaching a couple of % of the speed of light, a binary star system, likely just a million years from merging. A handful of mysterious dust-shrouded objects that survived close encounters. Nobody expected them to survive, and possibly pending confirmation, a millisecond pulsar that could eventually let us map the curvature of spacetime itself with unprecedented precision. And contrary to 50 years of observations suggesting otherwise, this black hole is not, and has not always been, simply calm. Within the last 1,000 years, it blazed 10,000 times brighter than its current state, an event preserved only as a delayed light echo bouncing off a nearby cloud of gas, with earlier studies hinting at a longer, centuries, deep history of similar episodes. And right now, continuously, it's exhaling a faint but genuine wind, sculpting a 3 light-year cavity into the gas around it, exactly as 50 years of theory always insisted it must. Lay all of that out chronologically, and a kind of biography starts to take shape. A radio signal first noticed in 1974 with no clear identity. Decades of orbital tracking through the 1990s and 2000s, slowly converging on a mass and a location. A Nobel-recognized confirmation in 2020. A photographed shadow in 2022. a magnetic field map in 2024. A record-breaking close-orbiting star, a surviving binary, a possible pulsar, all turning up within the same few years of intensifying observation. And finally, in 2026 alone, two separate confirmations, one of a violent past, one of a quiet but real present-day wind, that together overturn 50 years of assuming this black hole simply doesn't behave the way its cousins do. It's not an exaggeration to say that more has been learned about the fundamental nature and behavior of Sagittarius A in the last 8 years than in the previous 50 combined. Whether all of that activity stems from a genuine black hole, with all the strange physics an event horizon implies, or from something stranger still, a dense knot of invisible matter we don't yet fully understand, remains, technically, an open question. But it's an open question resting on an extraordinary foundation of confirmed, hard-won evidence, assembled over more than 50 years by multiple independent teams, using completely different instruments, methods, and lines of reasoning that have nonetheless converged again and again on the same broad picture. That more than any single discovery covered in this video might be the real story here. Not one dramatic breakthrough, but the slow, cumulative process of science working as intended, hypotheses tested, instruments improved, alternative explanations taken seriously and rigorously checked, decade after decade, against an object that has made astronomers earn every single piece of evidence they've ever gotten from it. Sagittarius A was never going to give up its secrets easily. 26,000 light-years of distance and a galaxy's worth of obscuring gas and dust saw to that. What's remarkable isn't that mysteries remain. It's how much has been pried loose anyway, one stubborn measurement at a time. Step back now far enough to see the whole picture at once. Every star you can see in the night sky, every planet in our solar system, our entire sun included, is in motion around the object this video has spent the last several hours describing. We've been orbiting it for the entire history of our species, as part of an orbit so vast it takes our solar system roughly 225 million years to complete a single full circuit around the galactic center, a journey so long it predates the dinosaurs. And one we are still only partway through. For nearly all of that time, we had no idea Sagittarius A was even there. For most of human history, the galactic center was just a brighter smudge of light in the constellation Sagittarius, unremarkable, unexplained. It took radio astronomy to find the first hint of it in 1974. It took decades of painstaking stellar tracking to confirm what it actually was. It took a planet-sized virtual telescope, built from instruments on multiple continents, to finally see its shadow. And it took until this very year, 2026, for two completely independent teams, using two completely different instruments, to finally catch it doing the two things theory always insisted it must be doing: flaring and exhaling. There's something genuinely striking about how recent all of this is. If you're watching this video as an adult, it is entirely possible that you are older than confirmed scientific knowledge of what, exactly, sits at the center of our own galaxy. The Nobel Prize confirming Sagittarius A's basic nature was awarded in 2020. The first photograph of it is younger than many smartphones currently in use. The wind theory predicted for 50 years was only confirmed weeks before this video was written. We are not looking back at ancient history when we study this object. We are watching genuinely new chapters get written in close to real time about the single most massive, most consequential object in our entire galactic neighborhood. Consider the contrast for a moment. Humans have known the broad outline of our own solar system's structure for centuries, that planets orbit the sun, roughly how many there are, roughly how big they are. We have known any of this about the center of our own galaxy for less time than many people alive today have been alive. The Earth itself is about 4 billion years old. Multicellular life is roughly 1 billion years old. And yet confirmed knowledge of the object every one of those organisms has spent their entire existence orbiting is barely a few decades old, dating, for all practical purposes, to sometime after most of the people reading this were already born. Consider the contrast for a moment. Humans have known the broad outline of our own solar system's structure for centuries, that planets orbit the sun, roughly how many there are, roughly how big they are. We have known any of this about the center of our own galaxy for less time than many people alive today have been alive. The Earth itself is about 4 billion years old. Multicellular life is roughly 1 billion years old. And yet confirmed knowledge of the object every one of those organisms has spent their entire existence orbiting is barely a few decades old, dating, for all practical purposes, to sometime after most of the people reading this were already born. Put it another way, our solar system has completed roughly 20 full orbits around the galactic center since Earth itself formed. We are right now partway through the same orbit our solar system was already deep into when the first complex animals appeared in Earth's oceans, hundreds of millions of years before anything resembling a dinosaur, let alone a human, ever existed. Sagittarius A has been quietly anchoring that orbit for the entire span of life on this planet, indifferent to every mass extinction, every ice age, every species that has ever risen and fallen here utterly unaware in any meaningful sense. That we exist at all, and we've only known its name for about 50 years, and there's still more to learn. The pulsar candidate found earlier this year remains unconfirmed, waiting for follow-up observations that could, if it pans out, hand astronomers their most precise gravitational laboratory yet. The dark matter alternative remains technically alive, waiting on instruments not yet finished being built. The molecular clouds scattered around the galactic center are still out there, holding still more echoes of still older flares, waiting for someone with a sufficiently precise telescope to read them. Sagittarius A has spent 50 years teaching astronomers that patience, eventually, gets rewarded, that an answer can take half a century to arrive and still be worth the wait when it finally does. We are, all of us, quietly circling something we have only just begun to understand. It has taken human civilization the better part of a century just to confirm what it is. It may take considerably longer to learn everything it's actually capable of. The next flare, whenever it comes, might not need to wait 1,000 years to be noticed. The next echo might be sitting in a molecular cloud astronomers haven't even pointed a telescope at yet. And the next image, sharp enough to finally catch a photon ring or rule it out for good, may arrive sooner than any of us expect, from an instrument that, as of this video, hasn't even finished being built. 26,000 years from now, the light leaving Sagittarius A tonight will finally reach some future telescope, built by people we can't begin to imagine, asking questions about this same object that we don't yet have the tools to even formulate. Whatever they find waiting for them in that light, it's a fair bet it'll be just as strange and just as humbling as everything covered in this video has been. For now, what we have is this, a black hole. Or something close enough to one to have fooled nearly every test we've devised, sitting at the dead center of everything we call home 4 million times heavier than our sun, 26,000 light years away, quietly governing the path of every star in the sky above you tonight. 50 years ago, we didn't know its name. Today, we know its mass, its shadow, its magnetic fields, its strange neighbors, its violent past, and its gentle, ongoing breath. That's not a small thing to have learned, about the one object every single one of us has been orbiting since before we were born and will keep orbiting long after we're gone. If you made it this far, thank you for spending this much time exploring one of the strangest objects in our galaxy with us. If you'd like to see more deep dives like this one, consider subscribing and let us know in the comments which corner of the universe you'd like us to explore next.